Good morning, everybody. I am Mohammad Rizwanur Rahman. Today I am going to present my research topic, electron paramagnetic resonance and dynamic nuclei polarization of 29 silicon nuclei in lithium-doped silicon. Our collaborator K.M. Ito, L.S. Velasenko, and Eugene Haller. Okay. Why lithium? Lithium donor electron has shorter electron spin relaxation time than phosphorus. High electron and nuclear spin polarization is absolutely necessary for the development of spintronics and quantum computer. Dynamic nuclear polarization due to phosphorus is not effective at low temperature. We expect that the saturation of lithium EPR line at low temperature give higher 29 silicon nuclear polarization. Our motivation, application of lithium in spintronics and solid-state quantum computer, better understanding of dynamic nuclear polarization property of lithium in silicon. Dynamic nuclear polarization. As we know that silicon has 3 isotopes, 28, 29 and 30. Only 29 has nuclear spin. Here 29 silicon up nuclear spin represents the magnetic quantum number plus half and down spin represents minus half. In bulk silicon, when there is no magnetic field, no net magnetization exists. But in the presence of magnetic field, net magnetization exists. Polarization is defined by simple mathematical equation. Total number of down spin, nuclear spin minus total number of up nuclear spin divided by total number of nuclear spin. At 3K and 1 Tesla, the thermal equilibrium value of electron spin is 96.5, while thermal equilibrium of nuclear spin is 0.06%, which is quite low. So if somehow we can use the polarized electron spin to polarize nuclear spin system, that process is called dynamic nuclear polarization. Mechanism of dynamic nuclear polarization. I will explain the solid effect because in my sample I observed solid effect. Solid effect. This is the thermal equilibrium diagram of electron and 29 nuclear spin system. Here you can see the population of down electron spin to ratio of population of electron spin up is 3:1. In case of 29 silicon, up to down is 1:1. This T1E represents the T1 time of electron spin, T1N represents T1 time of nuclear spin. This transition is flip-flop. Transition between these two levels are flip-flip transition, and transition between these two levels are Elort transition, and transition between these two levels are flip-flop transition. Flip-flop and flip-flip transition are forbidden transition in EPR. When we saturate one of our forbidden transition here, first we saturate flip-flop transition. The population level between these two levels become equal, and due to the short electron spin relaxation time, electron will relax and redistributions occur, and you can see the enhancement in the down nuclear spin occurs. So you can see the polarization of nuclear spin when you polarize flip-flop transition in positive direction. The same phenomena occurs when you saturate second forbidden transition, flip-flip transition, and the population of 29 nuclear spin in up direction increases and negative polarization happens. So saturation of forbidden transition leads dynamic nuclear polarization. Now I will explain about my experimental result. Sample information. Lithium was diffused into floating zone natural silicon. I have two samples, sample 1, sample 2. Sample 1 is lithium oxygen complex, which shows trigonal site, and isolated lithium, which shows tetragonal site. Both has donor concentration of 10 to the power 16. EPR line shape and G factor of lithium. I have very interesting result. Feher was the first person who tried to detect isolated lithium in floating zone, but he didn't observe, but Watkins observed, but under stress condition. In my sample, I observed isolated lithium without external stress. We recorded the angular dependence with the help of reference sample of phosphorus at 3.2 K and under illumination condition. Under illumination is used because phosphorus didn't show EPR line at such low temperature, so we have to use illumination to detect the phosphorus EPR line. Why we are able to detect the lithium EPR line without any external stress? Because we think that there is some residual stress in my sample due to the rapid quenching of my sample after diffusion. Experimental method. This is our X-band continuous wave EPR, Oxford helium cryostat, schematic diagram of Oxford helium gas flow cryostat. First, we observe the lithium EPR line and then saturate EPR transition with high microwave power at fixed magnetic field. This is our EPR line along of lithium along 100 direction. We saturate our flip-flop saturation at 323.17 millitesla with 200 milliwatt microwave. After saturation of T time, we transfer our sample to pulse NMR and apply pi by 2 pulse to detect 29 silicon NMR signal. Here you can see the enhanced signal, and this is the thermal equilibrium at 7 Tesla and 300 K. You can see the thermal equilibrium value is around 85, and in the case of enhanced it is 10 K. So we can increase our 29 silicon nuclei polarization value by using this technique. Temperature dependence. I have very interesting results in temperature dependence part. First, you can see this figure. This is EPR intensity versus temperature. In the case of lithium oxygen complex under dark condition, and in the case of light illumination condition. In the dark condition, when we decrease our temperature from 10K to 3K, the EPR line decreases, but in case of lithium oxygen complex under illumination condition, it remains almost constant. We don't know yet what exactly the reason behind this, why the EPR line decreases, but when we observe the NMR intensity versus temperature, we record the almost constant NMR signal in the range of 3K to 10K in both condition, under illumination and under dark condition. It shows that in the range of 3K to 10K, first thing is electron spin relaxation time doesn't change, and second is it has short electron spin relaxation time, because we are able to detect the temperature EPR line at low temperature. The similar phenomena occurs, and almost it correlates with the phenomenon, the EPR intensity with the of dynamic nuclear polarization degree of degree of polarization versus temperature. Here also you can see the temperature dependence of degree of polarization is almost constant in lithium oxygen complex, in dark and in light also. In case of lithium, isolated lithium, it shows very normal phenomena, like at low temperature, when you decrease the temperature, EPR intensity increases and NMR intensity decreases with increasing temperature. So I would like to conclude that in contrast to the phosphorus, lithium oxygen complex under illumination and isolated lithium, EPR absorption line intensity increases with decreasing temperature, which shows short electron spin lattice relaxation time, and degree of polarization correlate with temperature dependence of EPR line intensity of lithium oxygen complex and isolated lithium. Now, power dependence. Here, in both the sample, isolated lithium and lithium oxygen complex shows inhomogeneous broadening behavior when we when we saturate our EPR line. Inhomogeneous broadening gives information about differential solid effect. Now I will explain, I will show you my field dependence data. Field dependence of lithium oxygen complex. Here you can see the y-axis represents the normalized EPR intensity and NMR intensity. X-axis represents the B-sat minus B-naught. B-sat is the saturation field where we saturate our EPR line. Each red dot or blue dot represents the saturation field, and B-naught is the center field. In case of lithium oxygen complex, magnetic field parallel to 100 plane under dark condition, you can see the maximum intensity observed at the peak point of the EPR line. This shows that the flip-flip and flip-flop transition occurs exactly at the peak point. So this gives the information about differential solid effect. And in rest 3 condition, lithium oxygen complex, magnetic field parallel to 110 under dark condition, and lithium oxygen complex under 100 under illumination, and lithium oxygen complex under B parallel to 110 under illumination condition. All 4 shows differential solid effect behavior. Now I want to show you about isolated lithium. Isolated lithium has very interesting features. First is, in case of lithium oxygen, isolated lithium, magnetic field parallel to 100 plane, it shows the differential solid effect behavior. But in case of isolated lithium, magnetic field parallel to 111 plane and magnetic field parallel to 110 plane, it shows resolved solid effect. This is because the peak to peak width is shorter than the B0 minus G n by G. It means the flip-flip and flip-flop transition does not exist at this point. It exists from here to here, which is almost 2 Gauss. This distance is 2 Gauss in both the case. So again I want to conclude, we observed dynamic nuclear polarization by solid effect in both lithium oxygen complex and isolated lithium sample. Differential solid effect was observed in lithium oxygen complex, magnetic field parallel to 100 plane and 110 plane, and isolated lithium, magnetic field parallel to 100 plane, while isolated lithium shows resolved solid effect in B parallel to 100 and 111 plane. Now I want to show you the temperature dependence. Temperature dependence, time dependence. I measure time dependence of lithium oxygen complex in the dark under illumination condition and isolated lithium in dark condition. The maximum enhancement In lithium oxygen complex, we measure not enhancement, polarization, we measure 0.72%, and in the case of lithium oxygen complex, in 11 plane in 0.36%. As compared to phosphorus, it was both the polarization value is higher than the phosphorus, because polarization value depends on the temperature condition. So when we polarize at low temperature, we expect that the higher polarization will occur, and we observe this phenomena. This data was recorded by Hayashi in our lab. We can increase this polarization value to some extent, this and this. As I said earlier that in both the sample, we observe the differential solid effect behavior. So how differential solid effect and inhomogeneous broadening affects our polarization value, I want to show you that part. Inhomogeneous broadened line. This is the Gaussian shape of normalized Gaussian shape, which has half width h half, and it consists of several spin packets whose rectangular width is chi. When we polarize at h naught value, there is polarization, some polarization in flip-flip direction and some polarization in flip-flop direction. So there is a partial polarization which is called P plus, and partial polarization P minus, due to the superposition of several spin packets. So there is a reduced enhancement which is defined by P plus plus P minus divided by P naught, and which is proportional to dG by dH, means the first derivative of EPR line, which I show in the previous case, that in my field dependence case we have first derivative of polarization value. So to avoid inhomogeneous broadening line, we can use isotopically controlled silicon. Now I want to conclude my talk. We detect lithium, isolated lithium in floating zone silicon without external stress. Diffusion of lithium in floating zone silicon, diffuse lithium in floating zone silicon forms lithium oxygen complex. After annealing, lithium, isolated lithium and lithium oxygen complex has shorter electron spin relaxation time. DNP is dominated by solid effect in lithium oxygen complex and isolated lithium. We observe maximum 0.72 degree of polarization and 333 enhancement in lithium oxygen complex under illumination condition, and polarization time was 3 hours. Thank you for your kind attention.